Hey there, everybody. Today's day two, part two of day 5. Part 1 yesterday talked about absolute convergence. Today we're going to talk about this cool thing called power series and radius and interval convergence of power series. So let's get started. So a power series is actually, no pun intended, but a very powerful thing. And I want to talk about the most general of the power series and how it kind of links back to geometric series and its uses and all that good stuff. So this series right here, which we would have go on to infinity, can actually be represented using the following notation. So let's take the sum from n equals something to infinity of x to the nth power. Okay, so up until this point, we've been starting at n equals 1. In power series, we want to start at n equals 0. It's pretty cool. As you look at it, x to the 0 is 1, x to the 1 is x, x to the 2 is x squared, etc. down the line. This, most likely, if you're kind of wondering, wow, that looks geometric, almost. You're absolutely right. It does look geometric. Like, imagine you have 1/2 to the n. Does that series converge? Yes. Or 1/3 to the n, or 2/3 to the n. Right? And that converges for certain values of that r value. Right? So if we look at this right here, I don't have a number of x, so that's very foreign to us. But scratch this, I want to get rid of that. It doesn't, right now I don't care about that. But if I'm looking at this as a geometric series, right, what are the two important things for me to find the infinite sum? Well, for me to find the infinite sum, right, we've used this formula. We need to know a and we need to know r. Well, in this case, a is 1 and r is x. This is a really cool link, but this series representation right here can actually be written in function form. So let's talk about why this is important, right? Because we might be given functions like, I don't know, I'm going to make one up, but something like this, right? And in order to integrate that, wouldn't it be nice if it came in a form like this, as a polynomial? Or if I wanted to take the derivative of that function, wouldn't it be really nice if it were in polynomial form? So having power series representation and a power series expansion, which is what that is actually very powerful. So what we want to do is we want to be able to take a power series, turn it into a function, or a function and turn it into a power series. The other thing I want to highlight here before I move on is that when we talk geometric, right, what do we want r to be? In order for a geometric series to converge, we want r, the absolute value of r, to be less than 1. So you can almost think as this about this x, right? This x right here, as like our potential radius of convergence. And there might be some other pieces attached to it, a coefficient, or it might be divided by something. But basically what we're going to do is we're going to find the values of x that will make a power series converge. Okay, the values which will allow us to have a convergent series. And then we're going to, find that radius and then find that interval around what we'll call the center of that interval of convergence. So let's get started with a couple of examples. All right, so let's express this one first. All right, I have 1/5 minus x. Right, that's my function. I want it to look like this. I want it to look like f of x equals 1/1 minus x. Okay, I have to have this be a 1 and this be a 1. And this could be some form of x. Right? So how could I do that? Well, I'd take this, and I like the 1 in the numerator, but I got to get that 5 out of there. That means I'm going to have 1 minus x over 5. Now this right here, the 1 over 1 minus x over 5, takes on a very similar form to this kind of parent function that we're working with. So I can write a series representation, power series representation from 0 to infinity of 1/5, that comes from this 1/5 here, right, times x over 5 to the nth power. And that can be cleaned up just a tiny bit. Let's do so. Alright, that would be x to the nth power over 5 times 5 to the nth power. So 5 to the first times 5 to the nth, which also can be simplified to be the following: x to the nth over 5 to the n plus 1. So that would be a power series representation of this function right here. Okay, let's try another one. F of x equals 1 over 3 plus x. I could write that as 1 over 3 times, now notice this is plus, not minus anymore, so that'd be 1 minus a negative x over 3. Right, I had to factor out the 3 and change that to a negative. Therefore, the power series representation there would be 1/3, okay, negative x over 3 to the nth power. I'm going to clean that up. Watch what I do here. I'm going to take the negative out, turn this into an alternating series. I'm going to take x to the nth and take that over 3 to the n plus 1. There's your power series representation of that function right there. Okay, and the last one, let's take a look at that, and then we'll talk radius and interval of convergence in a moment. Alright, so I can factor out a variable. I'm going to factor out an 8 as well. That leaves me with 1 over 1 minus a negative x over 8. Okay, so the summation notation on that would be the following. And that can be cleaned up as well. So it's a bit mind-boggling to think that these two would be equal, but there are some parameters on when they're equal, right? When that function can be represented by this power series. Let me finish this up real quick. X to the n times x to the second would be x to the, oh goodness, what was that? X to the n plus 2 over 8 to the n plus 1. Here's your power series representation. Now there's two things that need to happen. First of all, this has to be an infinite sum, right? So it has to be infinite in nature, meaning that that's got to go to infinity. The second thing is that x has to be some value such that this series converges. It only works if it converges. Okay, so for in our original example, when we went from 0 to infinity of x to the n, x had to be, absolute value of x had to be less than 1, right? It had to be convergent. Okay, so that brings me to this idea of radius and interval of convergence, which I want to touch on, and I believe in the homework problem. So let's get there. Okay, so I want to touch on number 3 here. First, I'm going to write this as a power series. F of x would be 3 times 1 over 1 minus 5x. So that's in a good form. So what that would be is from n to 0, or n equals 0 to infinity of 3 times 5x to the nth power. Okay, let's pause there for a moment. So now I'm going to jump into this radius of convergence idea. And the radius of convergence comes directly from the ratio test. Okay, and you'll recall that with the ratio test, we wanted it to come out to be less than 1 in order to be convergent. So I'm going to take this and do the ratio test on it. Okay, so I'm going to do this, limit as n goes to infinity of the absolute value, which would take care of any alternators, in this case it doesn't matter, and divide it by x to the n, right? 5x to the n. So let's clear this up a little bit. We could clearly cancel the 3's. So I'll be left with 5x to the nth times 5x over 5x to the nth power. Okay, so the limit as n goes to infinity, these clearly would turn into, they would cancel. So as n goes to infinity, I would get the absolute value of 5x. Okay, x is not dependent on this limit, right? Because the limit is as n goes to infinity. Therefore, I want this thing to be less than 1. The next thing you want to do is you want to isolate x. Therefore, the absolute value of x would be less than 1/5. Right there, you have your radius. Your radius of convergence is 1/5. And it's centered, right, around 0. So if I took the absolute value away, this is our potential interval. Okay, so this is, I'm not going to say our interval, because what we'd have to do, and we're going to do in the days to follow, is we'd have to check to see if these endpoints would work, right? So I don't know for sure, but how I'm going to write this then is I know my radius is 1/5. My interval of convergence, I'm going to write with kind of this, I don't know for sure. I'm just waiting until my teacher tells me what the heck to do. So that would be our interval of convergence. Now tomorrow, we'll confirm whether or not these are closed or whether they're open, right? We'll figure all that out tomorrow as we test endpoints. All right, but that's how we do our interval and our radius of convergence. Let's try that on one more example. Okay, so let's do this. Let's do this middle one here. I want to write out the function notation for this. If I wrote out the first couple of terms, this thing to the 0 power would be 1. That thing to the first power would be that thing. That thing to the second power would be that thing yet again to the second, right? So f of x could be written as first term over 1 minus the common ratio, 2 minus x. Okay, so that would be our function notation. Alright, now in order to get the radius of convergence, we're going to employ the ratio test. Okay, so the ratio test would tell us that the limit as n goes to infinity of the n plus 1th term over the nth term, we want to be less than 1. Okay, so as we do this, what you may already have figured out, but maybe some of you are still working through some of this, is that we would get 2 minus x, but to make it clear, I'm going to go 2 minus x to the nth times 2 minus x to the first over 2 minus x to the nth. So these two terms, as n goes to infinity, will just negate each other, and we get this absolute value of 2 minus x equals, oops, I want it to be less than 1. Alright, so at this point, our radius of convergence is 1. However, it's no longer centered at 0 like the last one was. So if I take out the absolute values, I get the following, and now I'm going to find my center. This is where you need to be careful. I'm going to subtract 2 from both. And then when I negate this and make it a positive, right, make it a positive x, it's going to flip each of those. Okay, so that'd be from 1 to 3. So it's kind of goofy, but our potential interval of convergence, I'm going to just dot these for today, would be from 1 to 3. And notice the center of that would be at 2. Oh, go figure, right? Alright, so that's just a nice little intro to radius and interval of convergence. I think I'm going to do one more problem on the next page because it's kind of goofy. So you can hang around for that or call it a day. Alright, so let's look at this one. We want the interval of convergence, which means we need to find the radius first. So I'm going to employ the ratio test. So the limit as n goes to infinity of 1 over x to the 2 times n plus 1 over 1 over x to the 2n. Right, I like the way that this is going to work out. I'm going to multiply by the reciprocal of the bottom. If I do so, on both top and bottom, I'm going to get the following. Okay, which I can work with. Okay, so that would be x to the 2n over x to the 2n times x to the 2. So as the limit goes for n goes to infinity, those will go away, and I'll get 1 over x squared. In order for this to converge, I want that to be less than 1. At this point, the radius will equal. So as I look at this, think about this for a moment. I want 1 over x squared to be less than 1. In order for that to be true, x would have to be greater than 1. Or x would have to be less than negative 1. Alright, so test that for a second. Let's pick a number greater than 1. Let's go with 2. Plug in a 2. 1/4 is less than 1. Good. Okay. How about negative 5? Negative 5 squared, 1 over 25. We're good. That'd be less than 1 as well. So our interval of convergence is a goofy one. Our interval of convergence will be from negative infinity to negative 1. I'm going to put that there, as well as from 1 to infinity. That's a crazy one, you guys, but it's got some good stuff buried in there. I would feel real good if you were getting there. I'd feel real good if you were getting to this point and not even knowing what the radius was there. But that's a good intro to radius and interval of convergence and power series. Have a good one.